Thank you, Laura. Good afternoon, everyone. So I will start with I would like to thank the people on this slide who helped me designing this presentation, either by providing me some materials or discussing with me about the content, and a special thanks to Laura for inviting me here. So this presentation will be twofold. In the first part, I will tell you about the basic concepts and the syntax of OpenMP. So if you're already familiar with OpenMP, it's the right time to check your email. And during the second part of the presentation, I will illustrate the actual execution of an OpenMP parallel program on some multiple machines that is complicated enough, so we have a problem with it. So let's start with the basic concept of OpenMP. So what is OpenMP? OpenMP is the de facto standard API to write shared memory parallel applications. So it's not a language per se, but it's an extension of the C, the C++, and the Fortran language. And it consists of a set of compiler directives, runtime routines, and environment variables. The specification is maintained by a group called the OpenMP Architecture Review Board. So this group is made of several industrial and academic partners. And you can have the list of the people involved on the openmp.org website. So the current version of the specification is 4.5. It's been out since November 2015. So these are the advantages of OpenMP advertised by the people who designed it. So OpenMP is a mature standard because it's been out since a long time now. It's considered to be portable because it's supported by a wide variety of compilers, and it has been ported on many architectures, even emergent architectures. And one of the key steps here is that OpenMP allows, like many directive-based approaches, incremental parallelization. So this is very important because this means that if you have your favorite application that is a sequential application and you want to make it parallel, you can focus on a specific part first, try to do the best out of this part into parallelization, and then move your focus to a different part. So this is quite different from other approaches like message passing. So another advantage of OpenMP is that it imposes low to no overhead on the sequential version of your program. If you want to get back to your sequential program, you just have to tell your compiler to ignore the pragmas. And it's supported by some wide and active community. So since revision 3.0, OpenMP is moving really fast. So if you heard about OpenMP, about parallel regions and loops, there are many more features now. And I will tell you more about tasking, but there are also support now for accelerators. So this is the first OpenMP example I will show. This is definitely the worst example ever because it's not computing anything, but it's just for you to understand the way OpenMP applications are designed and executed. So all my example will be in C, so I'm sorry if you're not fluent in C, but it's really basic C. So if you have any questions, I can help you understanding this. So basically, OpenMP follows a four-gen execution model, which means that you start a serial program, and then your program goes parallel. You will create some threads that will compute something, and at the end of what we call here an OpenMP parallel region, this thread will terminate, will be joined, and that's we call the join aspect here. So any statements executed outside parallel region are executed sequentially. So you have a sequence of serial code, then parallel execution, then serial execution, and so on. So about the OpenMP memory model, you have two different logical memories in OpenMP. You have the shared memory that can be accessed by every thread of an OpenMP parallel region. And you also have some private memories that can only be accessed by the corresponding thread. So it's a thread private memory, per se. OpenMP is a shared memory programming model. So this means that data transfer is performed through shared memory and is completely transparent to the application. And it's up to you, to the application programmer, to annotate the variables to express that these variables are shared and these variables are only private, for example. So to do so, you have some data sharing attributes. The most famous ones are shared and private. So shared, if you label data to be shared, this means that this data can be read and modified by any thread of the parallel region. Everyone will see the modifications of this data. If the data is private, this means that every thread will have a copy of this data somehow, and we'll work on this copy, and no one can see the modification, except the thread that is attached to this private memory. And you also have some declination of private, which are first private and last private, that basically tells you what value you should initialize your private data with. So this is for first private. I will not tell you about last private because I won't use it in the presentation. Okay, so now you know how to create threads, which is a good start, but you don't know yet how to put them to work. And this is done. This can be done with the OpenMP4 construct. So OpenMP4 is one of the most popular constructs in OpenMP. This is, I think, the main reason why OpenMP has been so widely adopted. And basically, OpenMP4 is here to distribute the iterations of the following loop to the threads that have been created here. So there are many ways to distribute these iterations over the threads, and you can decide the way it is distributed by specifying what we call an OpenMP loop scheduler. So if you don't specify anything, it will call what we call the static scheduler, which basically will divide this iteration range into the number of processors that you have on your machine. So basically, on this example, every thread will compute n divided by p iterations. Another thing to note that is important for the following of the presentation is that you have at the end of an OpenMP loop an implicit bias synchronization, which means that every thread will wait for the other thread here before continuing the execution of the program. Okay, so more about the OpenMP loop schedulers. So the static scheduler is the default one. If you don't specify any scheduler, you will end up using this one. You also have a dynamic scheduler in which you take all the iterations, you put them into some queue, and the thread will steal iterations from that queue. So it's a dynamic way of executing a loop, and it can be very efficient on loops with irregular code. You also have some guided scheduler. I will tell you more in a few slides. And you can also defer the decision of the scheduler choice at runtime. So if you specify scheduled runtime here, this means that the compiler doesn't know about the scheduler you will be using, and you will specify the scheduler when you run your application. Okay, so an example of assignment of iterations using OpenMP loops. Let's take, for example, this loop of 16 iterations ranging from 0 to 15, and execute them on a parallel region involving 4 threads. If you don't specify anything, you just put OMP4 on top of the loop, you will end up assigning chunks of iterations of size 4 here. So the first 4 iterations will be assigned to thread 0, the following 4 iterations to thread 1, and so on. You can also modify this default behavior by specifying what we call a chunk size. So a chunk size will be the size of the chunk that will be assigned to each thread. So if you use a static scheduler using a chunk size of 2 in this example, you will assign iterations by pairs, and when you are done assigning the first sets of iteration here, you will continue using a round-robin strategy. Another example of OpenMP loop schedulers with a loop involving 500 iterations on 4 threads. So if you use the static scheduler, you end up with something like this, which is pretty much the same thing that I presented on the previous slide. If you use a dynamic scheduler with a chunk size of 5, this means that you will divide your loops in chunks of 5 iterations, put all the chunks into some kind of stack or queue, and the threads of the OpenMP parallel region will steal chunks to execute the whole loop. Okay, so it's very dynamic, you can see here. And guided behaves just like dynamic, so except that the chunk size will decrease to a specific size, which is 5 here. So you have big chunks at the start, and you end up with assigning very small chunks that are close to the number that you provided here. Okay, so I told my presentation was a gentle introduction, so I have some very dummy examples, but because I didn't want you to be scared about some very complicated stuff. And the first one will be to parallelizing this using OpenMP. So the first thing you have to do is not the easiest thing, is to create the OpenMP parallel region to activate the threads. Why isn't this very easy? Because you have to specify the visibility of your variables. So this can be painful. And so remember that every OpenMP construct comes with a default behavior. And if you don't know them by heart, because they can be different from one construct to another, you can use the default none here to tell the compiler to help you defining them. Basically, default none means that if you forget some variable that appears here in the block of code, the compiler will return an error. Okay, so it's not much of a help, but it still helps. Okay, so here I have my threads created. I have defined the visibility of each variable that appears here. But for now, all my threads are executing the whole block of code, which is not what I expect from a parallel program. Basically, you won't get any speed up from this, because every thread will compute the whole thing. What you should do next is to put them to work using the OpenMP4 construct. So if you do so, the threads you created here will execute this for loop using the static scheduler, and then when every iteration of this loop are over, you can move to the second loop and so on. So with this, you end up with a parallel program that computes something that is correct, and you have some level of performance, but you can do better if you know a little more about the inside of the OpenMP specification. For example, here, remember I told you that the OpenMP4 construct ends with the barrier, so there is a synchronization between the threads here. And if you look closer at this simple program, you can realize that these two loops are completely independent. So there is no reason for threads to wait for each other here. They could start executing this loop. So you can express this using the no-wait construct. So no-wait basically removes the implicit barrier at the end of the loop. But if you do so, be aware that at some point you will need the thread to wait for each other, unless this statement will be computing anything. Okay. So this is what I call optimization number 1. You can do better if you consider that creating threads comes with a price, and putting them to work comes also with a price. So maybe there's no use to go parallel in here. Maybe it's better to execute this program sequentially. And you can express this using the if attributes of the parallel construct. So basically, you say here that if n is big enough and m is big enough, you can go parallel unless you run this in sequential. Okay. So it's not important to remember this. I just wanted to show you that most people that say that OpenMP is easy are stopping here. Okay. If you really want to dig into OpenMP, there are much work to do, and this will be some kind of the content of my presentation for today. Okay, so now I think many of you know about OpenMP loops already, but what if you have something to parallelize that does not can't be written with the loops? Okay. Imagine, for example, a recursive application. So this is not the best application you would parallelize also, but it's just a toy application, just to realize that writing this with a loop can be complicated. Okay. I mean, you will have to rewrite completely your application, and this is not what we expect from OpenMP. So you have some kind of tree of recursive calls here, and most of the time, to implement this kind of stuff in, let's say, nowadays parallel environments, you use tasks. So OpenMP supports tasks since revision 3.0. That has been out in 2008. So I can provide you with a list of versions of compiler that supports this and this constructs of OpenMP. So feel free to ask me after the presentation if you're interested. So the concept of tasking in OpenMP, basically you have one thread that will generate tasks. You can have several threads generating tasks, but the basic example is you have one thread generating task, and the other thread of the parallel region will pick some tasks to execute. Okay, so it's a completely dynamic execution model. Everything can run asynchronously, and you can perform. The runtime system can perform load balancing of tasks. Tasks can move from a thread to another. So the same example using tasks. So basically what you should do when you want to express task parallelism in OpenMP, you specify where the tasks are using the OpenMP task construct. So basically here I will create a task every time I have a recursive call to the fib function here. All tasks can be executed independently in this version. When a thread encounters a task contract, a task is generated, but it's not executed right now. It's asynchronous execution, so it's just generated. And these tasks you just generated can be executed by someone else. Okay, and you can't predict when it will be executed. It's completely dynamic. The only thing you can do if you need to be sure that all the task has been executed is to rely on the task wait construct, which will wait for the task you created here. Okay. So, like Jean-François said, how we implement task parallelism at the runtime system level. A common way of implementing this is to rely on the work stealing execution model. Basically, you have some stealers here that will pick some task from a task queue, and you have some workers that will generate the work to steal. So in OpenMP, each thread has its own task queue. So it's when I say in OpenMP, I should say in OpenMP implementation, in most of them, because it's not written as a specification, it's implementation defined, but each thread has its own task queue, and when you enter an OpenMP task contract, it pushes a task into your own queue, okay, into your local queue. And when you end up with no more work to compute from your local queue, you will try to steal tasks from other queues. So what's to remember here is that tasks are well suited to application with irregular workload because you have this load balancing mechanism between OpenMP threads. Okay, so now let's move on to your very first OpenMP tasking experience. That's another very compute-intensive program. So this program here, we want to use OpenMP to make this program print either a race car or a car race using task. Okay, and the battle plan is first to create the threads that will execute the task, and then to create the task and make one of them generate them. So if you take this serial program that you start from and you compile it and you run it using 2 OpenMP threads, of course, it will only print a race car because you hadn't created threads yet. Okay? So let's first start creating the threads that will execute the task with the OpenMP parallel region. Okay. Of course, if you run this with 2 threads, you have this kind of output. So the print statement can be interleaved, and you can have this kind of output here: erase, car. So the next step will be to create the task and make one of the threads and generate them. So to create the task, you will add the OpenMP task construct just in front of either your statement or your block of code. Here is just a statement, but it could be a block of code. And to make one of the threads that generate this task, you will use the OMP single construct. So basically, OMP single say that, okay, only one thread of the parallel region will compute this, will execute this. Okay? If you do so, you have a completely valid task OpenMP application, and if you run this, sometimes you will have erase car, and sometimes you will have car race. Okay? So now that you are a master of OpenMP tasking, we can do better. So imagine that you want to print a race car is fun to watch. Okay, you may disapprove with this sentence, but basically it's just for the example. So the more obvious thing to do is to add the 2 print statement here. And when you execute this program using OpenMP, the output can be disturbing. You have this kind of output. You have A is fun to watch, race car. So this means that this statement is executed first, then the 2 statements is fun to watch, and afterwards you will execute the OpenMP task. So to understand this behavior, you should know about the way OpenMP tasks are executed. So if you read carefully the OpenMP specifications, they define some what they call scheduling points. So basically, you have at the end of the parallel region, for example, you have what they call scheduling points. So the threads will reach this point, and if they reach this point, they will try to steal tasks to execute. Okay. So basically, what happens here is that the thread that will create the task will just create them and put in its queue, and this task will be only executed when you reach the scheduling points corresponding to the end of the parallel region. Okay, so this starts to be somehow technical, but you can also rely on an explicit way of guaranteeing that the task has been executed using a task wait construct. If you say so, the task wait, of course, is a scheduling point, and when a thread will reach this scheduling point, it will try to execute the task here. So this program will put either a race car is fun to watch or a car race is fun to watch. Okay?
Just a question.
Yes.
You put brackets, brace between the print A and before task wait, and you remove task wait. Do you have the synchronization?
No. No. Just by
put a block.
No. A block only is not sufficient. Okay, so what about dependencies with other tasks? So this is rather new, newer than OpenMP tasking. It has been introduced in OpenMP version 4.0, and this is what Jack presented this morning about the ability to express DAG, some kind of data flow parallelism in OpenMP. So let's consider this task-based application. You have some tasks that are created here. You have one task called task A that will modify variable X here. Task B will modify variable Y. And you have 2 tasks that will process either X or Y. Okay? If you want to make sure that task C won't start before task A is over, you have to put the task wait construct here. Okay, this is the main way of expressing this with OpenMP 3.0. So, but defining this comes with a problem because you will end up defining some kind of fake dependencies between tasks, because this also means that task, let's say task C, has to wait for task B also. But there is absolutely no dependencies between task C and task B. So you create false dependencies, which means that the runtime system is forced to respect them, and the execution of the program can run slower. So to express this with OpenMP, you can use the depend keyword. Yes.
In fact, you create synchronization.
Yes.
So you should declare dependency.
Yes. Yeah. But at the time, at this time,
You're just using a synchronization.
Yes. All right. So if you want to tackle this using OpenMP, the right way to do is to express dependencies using the depend keyword. So on the task, you can express that this specific task will read these variables, will write this variable, and will both read and write these variables. So you have the in, the out, and the in-out access modes, and you have several ways of several parameters you can pass to this attribute. Either a list of variables, it can also be, let's say, some kind of slice of a buffer. But and the syntax is basically the first element of the buffer and the size of the buffer you want to pass in the dependency. So if you remember the Cholesky example of from Jack this morning, it was using this kind of stuff. Okay. So the application programmer provides all this, and then it's up to the runtime system to decide whether a task should be executed or not, depending on the dependencies expressed on this task. This also means that if you, let's say, provide some wrong information unintentionally, this means that you will create some fake synchronization and you will have some bad performance. Okay, so if I take my toy example and apply the OpenMP 4 with dependencies version, basically I just have to say that I will write an X here, I will write an Y here, and I will read from X and read from Y here. So in this version, task C could be executed before task B, as long as the execution of task A is over, which couldn't happen in the version with the task wait stuff. So sometimes expressing dependencies helps unlocking more parallelism. You have more execution scenarios that can be achieved with this kind of stuff, and this means that the runtime system has a wider area of choices to make. Okay, so I'm done with this syntax. I don't know if you have any questions, so we will review some of the syntax in the second part of this talk.
Runtime, just execute the task as soon as possible when there are.
Yes,
all the dependencies are.
Yes, of course, yeah.
But there is no possibility to indicate some kind of priority.
Okay, so that is completely implementation defined. This is not yet in the specification of OpenMP, but some implementations start to look this way and to also provide some ways of attracting tasks close to the data they are working on and stuff like that. So the OpenMP IRB, the guys that are designing OpenMP are discussing the possibility of adding some priorities, some stuff like that. But for now, it's just implementation defined. Yeah.
So I have a question about the composability of that pragmat, right? So I write library code. So suppose the way you think about it, you say, I write a function, and inside my function, I'm going to have a pragma 4, right? And then that's going to be a library interface. And then someone else is going to call my function, and they might want to do pragma 4 on the outside.
Yeah.
I can't do intelligent resource management in that case. So what is the solution for that?
Okay, so the solution to this specific problem would be to use some other construct, would be task loop, where basically you say that instead of using OpenMP4, you will create tasks out of loop iterations, and tasks are easy to compose because either you are inside an OpenMP parallel region, and then task will be executed inside this calling function, or you are some kind of orphan task, and they will be executed sequentially. But the problem of composability in the more general way is a major issue. And there is a specific group inside the architecture review board that is discussing stuff about this, that is also speaking with people from the API forum, and so it's a hot topic. Yes? Yeah, OpenMP4 is available since GCC 4.9 and is also available inside the ICC compiler. You also can get the Clang 3.9 version of the Clang compiler that comes with the OpenMP runtime system that is open source and also supports OpenMP4 as well. Okay, so now let's move to you have written your OpenMP application and you want to experiment with it on your favorite platform. And the first thing you have to do, like Jack said this morning, is to understand your platform. This is mandatory if you want to achieve some good performance. And for example, what you should know about your platform is basically get information about the multi-core processor that is in it, how many cores are available, which of them are physical or logical cores when it comes to hyper-threading technologies. Also the memory hierarchy, which are the cores that will share cache memory, how is it organized on your platform, the architecture topology as well. You have some processors and you want to know how this processor will access memory. So these are pretty low-level details, and it can be painful to gather all these information. Hopefully you have some external tool that will help you do that. So this is the HWArc library. It's a library that will gather this kind of information from you and present them to you in a generic fashion. So this is my laptop, printed by the HWArc library. You can see that you have some hardware threads in here. You have 4 physical cores. Each of these cores have access to 2 different levels of cache. So you have a cache for instructions and data here, but it's a level 1 cache, and you have a level 2 cache. And all the cores in here will share a level 3 cache. And you also have the size of the caches, which can be useful as well when it comes to tuning your execution. It also reports the amount of memory that can be accessed by your multi-core processor here. And if you have a big machine, say with several NUMA nodes like this, it will present all the NUMA nodes that are on the machine. However, the thing that HWArc does not provide is what I call the entire architecture topology, which means it does not provide the way that sockets are connected together. So let's say the internal network topology is not provided, but on most operating systems, you can have some high-level information that you can use to infer this topology. So here you have a NUMA topology. So you have the memory. So this is a shared memory machine, but the memory is split in several banks, and each memory bank is attached to one multi-core processor. So this means you have some local accesses. You can also access memory that is located on a remote node that can be either close to you or far from you. And this information is expressed in a synthetic way with some kind of distances matrix. So this is the information you can have in your operating system. Basically what it says is that if you communicating on the local node costs 0, communicating with your neighbor is cost 10, and communicating crossing 2 hops here will cost 20. So these are fake numbers, but these are just to be able to somehow I have this in mind when it comes to exploit this kind of machines. Okay, so our testbed for today is the Intel 192 machine, which holds 192 cores. These cores are organized in 12 pairs of numenodes, so numenodes comes in pairs, and they are made of two 8-core Xeon processor, and with attached 32 gigabytes of memory attached to the processor. And this is a two-level NUMA topology. You have some pairs of NUMA nodes that are located 1 hop away from you, and others that are located 2 hops away from you. So it's a very hierarchical machine, and it can be tricky to get performance in this kind of, on this kind of machines. So the first part is some kind of reminder of the impact of cache memory on your application. This is not OpenMP related. This is not even parallel programming related, but it's as important as the rest of the talk. So just a reminder, when your favorite processor wants to access a variable in memory, basically, to access X here, you will load from the memory what we call a cache line. So a cache line is basically a predefined amount of memory. Most of the time it's something like 64 bytes. And a cache can be seen as a table of cache lines, okay? So accessing X will load the entire cache line holding X into the cache memory. And you will have what we call a cache hit if you access a data that is located in cache, so which means fast memory access, and we will have what we call a cache miss if the corresponding cache line is not yet in cache. And this, in this scenario, the hardware will load the cache line holding X to the cache, which ends up with longer memory accesses. So caches are very important if you want to exploit multi-core processors. So the first case study is some naive square matrix multiplication algorithm. The idea is not to write the best matrix multiplication ever. You are most likely to do so than me. But it's just to illustrate the behavior of caches on this kind of simple algorithm. So here I have a matrix C, and I want to compute the A times B and store it into C. So when we think about, so first let's implement this using OpenMP because that's why you're here. So you have this kernel that you will parallelize using an OpenMP parallel construct, and you will add the OpenMP4 construct to parallelize the outer loop here. And so basically it's only 2 pragmas. And when you run this, you use this command line. So I won't explain for now the OMP places equal cores, but I will soon. So this is the size of the matrix. This is the number of elements in a row on the Intel 192 machine. And I have this serial time, so something around 40 seconds. And in parallel, it runs at 0.2 or 0.3 seconds, which means this code will achieve 150 speedup, which is great because you only added 2 pragmas, okay? But this is not what you can expect from this program, obviously. And I want us to more focus on the execution time more than the speedup here, which is irrelevant to this application. So why I'm saying this? Because if you think about caches, and you know now that caches are manipulated through cache lines, let's assume that we work with 32 bytes long cache lines. And each element of the matrix is 8 bytes long, which is pretty convenient for my drawing, because this means that a row of the matrix will fit in cache, okay, will fit in a cache line. So the question is, how many cache lines do I need to compute one element of C, for example, C0 here? So to compute C0, I have to access A0, B0, A1, B4, A2, B8, A3, B12. So this first access will basically load the entire cache line here, just because I will access A0 here, okay? And the hardware will also load the cache line holding B0 to the cache, okay? There's nothing I can do about it. So when it comes to the second part of the computation, I access to A1, which is a cache hit. It's great, it's a fast memory access, but B4 is a cache miss, okay? And I have to load the entire cache line holding B4. And the same goes for the other Bs here. So as a conclusion, every access to A uses the same cache line to some extent for this computation, computing the first elements. So this is cache friendly, this is cool. But every access to the BJ elements use a different cache line, which can be a very poor cache utilization, because if this is wide enough not to fit in cache entirely, you will have some cache lines eviction. Okay, you have to replace, to make some room in the cache to load some other cache lines. So to deal with the BG situation here, the easiest solution would be to change the data layout of the matrix, just saying that, okay, I will transpose B, and if I transpose B, the B0, B4, B8, and B12 elements will be stored inside the same cache line, okay? So this kind of optimization is very dependent to the hardware, okay? I wouldn't do this if I hadn't some cache memory that is automatically updated by the hardware. But if you manage to do so, by changing, for example, the data layout or by blocking your algorithm or whatever, you can have some huge improvement in terms of execution time. So the serial time of this version is around 5 seconds compared to the 40 seconds of the first version. So, of course, this is compiled with all the compiled optimization, not maybe all, but at least O2 optimization and stuff like that. The parallel time is also smaller. The speed up is not great, but we have so much to do to improve this program. But if you compare this relative to this serial time, this is a time well spent from the programmer point of view. Okay, you have something like around 600 speed up. Okay, so this is very, let's say, direct application of the cache behavior on your program. Most of the time, it's not that easy. Okay, but this is something to point out. So the second stuff I wanted to talk about was controlling data placement on NUMA systems. So most multi-core machines now come with this kind of design, in which you have, from the programmer point of view, the memory is shared. You have a global memory. But from the physical point of view, this memory is split in several memory banks. And these memory banks are attached to different multi-core processors. And on this specific platform, you have some different latencies, or also different bandwidth. When you access the local node, when you access a node that is 1 hop away, and when you access the opposite node of this platform. So you can see that it's on this specific machine, which is some kind of a small platform. It's not the Intel 192 I presented before. You already have some 20% degradation when it comes to accessing a neighbor here, and you have something like 40%. And this can be different depending on if you read variables or write variables, depending on the cache policies and stuff like that. Okay, so how to deal with this as a programmer? It can be tricky, or it can be easy, depending on your application. Okay, so you can use some specific libraries to replace somehow malloc and friends, and to say that I want my buffer to be located on this node, if you are pretty confident on the fact that you need this to be located here. So it's very low-level way of programming. It's not very portable. You can also rely on your operating system, hoping that he actually implements what we call the first touch allocation policy, which is actually the default behaviors of most memory allocators now. So what is the first touch allocation policy? On most Unix-like operating system, when you call malloc or something like this, the corresponding memory pages are not physically allocated right now. Okay, there is some kind of lazy allocation. The actual allocation is delayed until the first access of the corresponding memory page, your variable per se. And the interesting part is that this memory page will be allocated next to the thread that performed the first access. So basically in the memory bank that is attached to the processor that is executing this thread. So in other words, this means that if you want to control data placement on your, in your application, and you want to rely on the first allocation policy, it's crucial to make sure that data is first touched by the thread that will access it during the computation phase. Okay? So to illustrate this, I will talk more about the stream benchmark. Jack told a little bit about it this morning. So stream is a memory benchmark written in C plus OpenMP that was designed to report aggregated memory bandwidth on any shared memory platform. And basically, here is one of the 4 kernels that is involved in the stream benchmark. And you can see that it involves very simple arithmetic operations on vectors. Okay. So the question here is how to initialize vectors A, B, and C to make sure the corresponding memory pages will be accessed locally when executing this kernel on a NUMA machine. So to do so, you will obviously use the first touch allocation policy, and you know that the first time that a thread will access the data, it will be allocated on its node. So this means you will have to initialize your data in parallel. Okay? So this is not about the performance of this loop, per se. This is more about the performance of this one. So what I do here is just to create some threads and so this is a contracted version of the OMP parallel, then the OMP4, okay? And I will initialize the data and make sure that the thread that touches it first will access it in the computation phase, okay? And this is basically guaranteed by the OpenMP specification. The OpenMP specification says that the same iterations will be executed by the same threads as long as both of these parallel regions involve the same number of threads, which is the case here because I didn't specify anything, so by default it will be the entire machine. And also the same number of iterations. And also using the same OpenMP loop scheduler, which is also the case because this is a default scheduler here, and it's static. So once we have here, we have, let's say, a first touch friendly kernel. Okay, so I will show you how important this can be in a moment. So now,
This could be difficult in C++ with initialization.
Yes, this can be difficult. Yeah. I totally agree with this. Okay, so now that you have this, what you should guarantee next is you want to make sure that a thread will be assigned to the same core in this region and in this region, because if you can't guarantee that, and you've lost, basically. And to do so, you will have to bind OpenMP threads. So the proper way of binding OpenMP threads is to let's say, use the OpenMP places. So places is a feature that has been introduced in OpenMP 3 something. So it's quite old, but it's becoming to be widely used. And basically, it's just a matter of standardizing things that programmers already have already been doing for years using some external libraries. Now it's up to the OpenMP runtime system to provide this kind of support, which is kind of a nice feature. So the first thing you have to do is to define what we call a list of places. So a place is a set of processing elements. So by processing elements, it can be some hardware threads, it can be some physical cores, or whatever. You can define this list using the operating system numbering. So if I create this list of places, basically this means that my places will be made of core 0, core 1, core 2, and core 3, for example, on my platform. And if you don't want to do so, and I'm pretty sure you don't want to do this, you can also use predefined abstractions. 5 minutes? Okay. Like threads, cores, and sockets. So, and then you have some ways of binding the threads on these places accordingly. So the default behavior is basically performing a round-robin assignment to the threads of the places. So about the stream benchmark, I ran the stream benchmark on the Intel 192 machine 20 times. And reported the performance on 3 different, let's say, versions. The first version is what we call serial init. So the vectors are initialized serially, which means that all the corresponding memory pages will be allocated on the same NUMA node. Okay, so I expected it to be bad. The same version when binding OpenMP threads, so they can move they can't move during the execution. Then let's say the official stream version, which is parallel init plus binding, and some in-between version in which you ask the HWArc library to distribute the memory pages over the entire machine to make somehow all the threads equally bad in terms of memory contention. So when you consider the first version, which is allocate all the memory pages of the 3 vectors on the same NUMA node, you have this kind of behavior. So this remind you that these are different executions of stream. You can see that there is a big variation in terms of performance, and also the best performance you achieve here is something about 11 gigabytes per second. When you bind the threads, you achieve some better performance, just because that the operating system doesn't need to bind the threads for you. Okay, here they only have 192 threads on 192 cores, but the operating system, if you don't bind the threads, still needs to do this for you, and can be costly. And at some point also you can have some thread migration from one core to another, which can degrade performance. So this is just about binding. Okay. Now we still have all the memory pages on the same node. Now, if you spread the memory pages on the entire machine, now you are beginning to have some real performance here. So remember that this is a blind spread of the memory pages on all the machine, which make all the threads equally bad in terms of memory accesses. Okay, it spreads out the contention. And if you do what you should do, which means a parallel initialization plus binding, you have some very stable performance, and you are about 700,000 megabytes here compared to the 11,000 megabytes. Okay, so of course, this is a toy application. This is a benchmark. You can't expect to have this kind of improvement in real-life application, but using this kind of technique, you can sometimes have something about 5 to 10% improvements on big platforms. Okay, so I'm short. I'm running out of time. Okay, 2 more minutes is enough. Because you already know about this. This is the Cholesky factorization that Jack told us this morning. So you are the expert here, not me. I just wanted to have some some discussion with you about the way this kind of OpenMP data flow program can be executed, and the role of the application programmer to basically keep what we call the runtime overhead at bay. So this is the corresponding code. It's not very important. The only thing that is important for me here is that this is a tiled version. Okay, so the number of tasks that you will create in here is proportional to the number of ties in your matrix. Okay, so this means when you run this on the Intel 192 machine and you vary the size of the block size of the tile of the block size, okay, you vary the number of tasks per se. You have some very different performance, okay, and this can be very tricky to set. This is this kind of parameter. This kind of what we call the parallelism grain. If you have very small ties, you will have too many tasks, and you will swarm the runtime system with tasks, basically. And if you have too big tasks, you end up with some load imbalance problem because you can't even the load on the machine. You don't have enough work to do that. So this is up to the application programmer should define the best block size, and it can depend on the architecture, of course, but also on the input matrix size and stuff like that. So this is, I mean, if you just run this and you obtain this kind of performance, you are not done yet. Okay, you have to tweak some of the parameters before completing. Okay, so I will just leave this slide here, and thank you for your attention because I'm late.
Thank you, François. Questions for François? Yes.
Okay, this is a NUMA placement question.
Mm-hmm.
So very often with what we do, the users are asking to break up an iteration space that's just a brick, right? Mm-hmm. So they want to eliminate halos. And so they're normally, it's not like the 1D stream, it's like a 2D or 3D thing. And so when they do that, if you naively lay it out in contiguous memory, you'll have false sharing.
Mm-hmm.
So what is the canonical OpenMP way to deal with false sharing for that kind of distribution?
OpenMP can't help you with false sharing.
Okay, so then you would have to like align it on cache
Yes,
line boundaries,
definitely.
and that will blow up your storage to the same as you would if you had shared none.
Yeah.
Yeah.
Other questions? So I have a question. Can you comment on why the scheduler in OpenMP that they just made available?
That is just, sorry?
That they made available, why it's so efficient? Do you know?
Which one? The task scheduler or the loop
Yes.
scheduler? So, yeah, because this morning Jack told you that the OpenMP scheduler was efficient, right?
Yeah, because they compared with
Yeah, to the
others and found out it's one of them.
Okay, so it depends on the OpenMP implementation mainly. So, for example, so I didn't have the time to show this slide, but this is a good opportunity. Here I compare what I call the runtime-related overhead of implementing the OpenMP construct for both the OpenMP GCC, the GCC OpenMP implementation and the Intel OpenMP implementation. So this is not to blame GCC at all. This is just to point out that nothing comes for free. Okay, you can add all the OpenMP stuff you want. This end up with creating some threads, with creating some tasks, with synchronizing them, with moving them from queues to another. And if you take, for example, the barrier construct, which is basically a synchronization between all the threads, This can be implemented in many, many ways. You have many algorithms to implement this, and depending on the machine you are running on, some algorithms will perform better than others. When it comes to execute tasks, it's the exact same thing. You have ways of execute tasks that will behave extraordinarily well on a small platform, for say. And you have some other way of implementing tasks that will perform well on some kind of static assignment of tasks in the queue, like most linear algebra, dense linear algebra problems are designed for. So my claim about this is that now the OpenMP task construct is mature enough so that the compiler and the runtime system can provide good implementations. For now, the Intel OpenMP implementation appears to be better because the task granularism is very, very small. You can create many, many tasks with a decent overhead. That's not the case with the libgamp new OpenMP implementation, but it was designed for another purpose, which is implementing the specification in 100% and be efficient on embedded system and stuff like that, in which you have less OpenMP threads and stuff. So you should definitely have a look to these two runtimes and take the one that suits your problem.
Okay, if there are no more questions, let's thank François again.